Okay, this is Jim Head. Welcome to the Solar System Exploration Research Virtual Institute course on the origin and evolution of the moon, co-sponsored by SSERVI, obviously, and myself, Jim Head at Brown University, and David Kring are the co-organizers of the course. Today we're really fortunate to have with us two experts, Gordon Osinski and Brandon Johnson, on lunar impact cratering and the formation of impact basins. This will give you a really good perspective. A lot of the questions that we've had from earlier discussions and lectures linked to the issue of the role of impact cratering. And of course, we know that although there's a number of impacts on the Earth, the lunar geological record of impact craters and basin formation is is unrivaled, basically, in accessibility and diversity. So both from a fresh crater point of view, large crater basin point of view, as well as degradation states and petrology, where we can actually go out and get the samples and understand them in context. So today we're going to hear from first Gordon, Ozasenski, and then Brandon. And Oz is got his PhD at the University of New Brunswick in 2004, and he's currently an associate professor at the University of Western Ontario. And Oz has a very remarkable background in terms of his research interest in impact cratering, ranging from a wide range of studies of impact cratering on the Earth and planets, and also integrating those together in terms of the petrology and understanding the fundamental processes of impact cratering. So we'll talk about these processes, and Oz will lead us through kind of a background on essentially lunar impact cratering, and then we'll go to Brandon, who will talk to us about larger basins and also modeling of these basins. We have very complementary backgrounds here, and we're really excited to learn today. So again, we'll do the hour, and then we'll have questions. So please post your questions in the chat box, and we'll address those at the end of both talks. I just want to point out that this is where we are today, October 31st. Happy Halloween to everybody. Next week, as we'll come back to at the end, before we sign off, we have Space Directive number 1, to the moon to stay. NASA Administrator Jim Bridenstine will, in fact, talk to us from NASA headquarters in person, and so we'll have a lot of really important insight into the coming years of exploration of the moon. So let me press on, and we'll now turn it over to Oz to talk to us about impact cratering on the moon. Over to you, Oz. Oz, we're not getting a.
Oh, sorry, I had my phone on mute. Can you hear me now?
Yeah, we're good.
Okay. Yeah, so it's a pleasure to talk today about lunar impact cratering. And I think, like many of the topics you've had throughout this course already, this in itself could be an entire graduate course. So this will be necessarily brief, and I'll try and give an introduction and an overview of impact cratering, and then again pass on to Brandon, who will talk about the formation of large impact basins. And so, I think as we look at the moon, it's preaching to the converted here. But as Jim said, the lunar impact cratering record really is unparalleled, and it is a natural laboratory for studying impact cratering processes. And even on a clear night without the aid of a telescope, we can see that the moon is pockmarked by impact craters. And we'll start off talking about some of these smaller ones, and then Brandon will take over and talk about these giant basins, many of which, of course, in this particular image are filled with mare. So let's start with some basics. We can divide the impact cratering process into 3 main stages: contact and compression, excavation, and modification. And right at the outset, I think it's important to highlight that impact cratering is unlike any other geological process. The timescales are very short, the energies involved are very large, and the strain rates are far greater than even the largest volcanic eruptions that we tend to see. And this is really because the projectile, whether it be an asteroid or comet, comes in anywhere from 15 kilometers a second or so to 70 kilometers a second for a comet. That is, of course, Earth. The moon, the impact velocities can be quite a bit lower, which does introduce some subtle differences that we can talk about later on if you're interested. So the contact compression stage, even for big basins, is short, typically seconds or tens of seconds. The projectile comes in penetrates 1 or 2 times its diameter, and then a shock wave radiates out from the point of contact, essentially between the projectile and the target surface. The shock wave radiates out into the target and back into the projectile itself. When that shock wave reaches the back of the projectile, this is what we call a free surface, and you can't subject such a surface to compression. And so that shock wave is then reflected back into the projectile and into the target in the form of a refraction wave or a release wave. So basically, by the end of this contact and compression stage, most of the projectile material is typically lost, either distributed around the planetary object in question or just lost back into space, and typically in the form of vapor or kind of mixed in with small melt particles. As we move into the excavation stage, it's the interaction of this outwards directed shock wave and the downwards directed refraction wave that opens up the crater. And so this is a big kind of discovery, as it were, in the 1970s and 80s, that the projectile doesn't mechanically excavate the crater. It's the shock wave that really does the damage. And so, for roughly speaking, a 1 kilometer diameter projectile, you end up with a transient crater, maybe 10 or so kilometers across. By the end of the excavation stage, as you're releasing the rocks from high pressure, we will do a lot of deformation in the rock that remains solid, and we'll talk about that later. That is in the form of shock metamorphism. And then we end up with a transient crater lined with melt. And this becomes important as we look at fresh craters, in particular on the moon. So for small craters on Earth, this cutoff is around 3 or 4 kilometers across. On the moon, because the gravity is lower, simple craters can be up to about 20 kilometers in diameter. We have, your characteristic simple impact crater. And so this is a schematic cross-section you're looking at here. We have a relatively deep crater, so relatively large depth diameter ratios. It's filled with a lens of material highlighted here in red, which is a mix of essentially broken up rock and impact melt. And that can vary from quite a lot of melt to quite a lot of broken up rock. And we'll look at those rocks are called impactites, and we'll talk a little bit about that later on too. In simple craters, we see an overturned flap, and then impact ejecta deposited from the rim outwards. And so, simple craters have been relatively well understood and I think accepted as being the products of hypervelocity impact for well over a century now. But it really took the discovery of shock metamorphism and the understanding that over a certain size threshold, they don't look simple anymore and they become complex. And so this was only in the 1960s and 70s, really, that we realized that again, above a certain size threshold, essentially the hole is unstable and gravity takes over. And so the walls of the crater collapse inwards, and then very critically, the floor of the crater uplifts to create what we call a central uplift. And that's kind of shown schematically in, at the end of the excavation stage and into the modification stage. And so I'm sure Brandon will touch on this later on and show it in some numerical models. But I do want to highlight here that, the cratering process is a continuum. If you were stood there witnessing an impact event, you would never be able to really put your finger on, when the contact compression stage ends and when the next stage ends. And even these two graphics kind of show that. So on the top image, you can see that the floor of the crater is beginning to uplift. So you've already kind of started crater modification, but the walls of the transient crater are still being excavated. And so there was definitely overlap in terms of these stages during crater formation. And also kind of shown on the bottom, and we'll get back to this later, crater modification results in, massive movement. And you'll see this when we look at some images of actual craters. The topography that we're talking about can be many kilometers high. And of course, material and the transient cavity can be many hundreds of kilometers wide for these big impact basins. And so that transports material. So this kind of red lining of broken rock and melt can be transported, moved around within the crater. Importantly, over the crater rim, and deposited for many hundreds, if not thousands of kilometers around. And so this leads us into what we call a complex impact crater. Typically, so this is a very simplified cross-section. If you ever go do field work at a complex crater on Earth, and hopefully we'll be doing this on the Moon again soon, you'll realize that this is a gross oversimplification. The rocks are heavily deformed in the crater interior, but it basically shows, we have what we would call a central uplift, and SU stands for stratigraphic uplift. So material there is brought from depth. There is then a relatively lower topography region where the allotronous crater fill deposits, again, mixture of impact melt and breccia, is lined. And then we have the collapsed or terraced crater rim, and then impact ejector. We'll talk about ejector in a little moment again too, but I do want to emphasize while we're on this slide, impact ejector is deposited beyond the transient cavity rim. In a simple crater, that transient cavity rim approximates the final crater rim. But because of collapse during the modification stage, in a complex crater, essentially you end up with ejector being deposited, and then the walls, and then crater collapse occurs. And so you can have impact ejector in this terraced region of complex impact craters. So as Jim said, I actually gave a talk yesterday at another institution out here about craters on Earth. And, it's not a good, Earth isn't a good place for studying the pristine morphology of impact craters, but, the Moon is. And so it's, a typical example of a simple impact crater on the Moon. And again, the diameter, they go up to about 20 or so kilometers, but there's a lot of overlap. A class of crater that hasn't received too much attention, though that's changing with a few papers in the last weeks and months, are what we call so-called transitional craters. So if I just skip ahead to your prototypical complex crater, so here's kind of the famous Euler Crater at 28 kilometers across. You'll see you have that beautiful blocky ejector blanket, a steep rim with a relatively flat crater floor. Good eyes, you see kind of lower albedo material surrounding that central peak. And so that darker material we interpret to be impact melt deposits. And then you literally have a mountain of a central peak in the very center there. And connecting these two are what we call transitional impact craters. And you can see you get the start of slumping. And in bigger transitional craters, you do get terracing. But a key distinguishing feature is that you have no central uplift. Of course, as we keep going, and I'm not really going to talk about this too much, we end up with peak ring craters, and then beyond that, we get into multi-ring basins. And what Brandon's going to focus on is that while we have a fairly good handle on the transition from simple to transitional to complex craters, how we move from central peak craters to peak ring basins to multi-ring basins, there's still quite a lot of debate. And again, I won't steal Brandon's thunder, and we'll leave that for him to discuss. Again, we could talk about so many things here, but I do want to highlight one particular aspect. It's a topic kind of near and dear to my heart in cratering studies here on Earth, but it is important to note the effect of target lithology also on the Moon. All rocks are not the same, and so the behavior and the finishing product in target rock on Earth and on the Moon are quite different. And this was a relook at diameter relationships by Jessica Kalin and colleagues from 2013. And this was basically revisiting Pike's work from the 1970s using, of course, data from the Lunar Reconnaissance Orbiter. And, it's quite a busy plot. There's big error bars, but what I really want to draw your attention to here is, the red circles and the green squares. And, even just from a distance, you can quite clearly see that the depths of craters in the mare, so in these volcanic plains materials, are considerably lower than from the highlands terrains. We have craters of the same diameter, and I'll show another slide about this in a second. But, in the mare, there's something like almost up to 2 kilometers difference in depth. Why that is the case is that, we're still looking at this. I think it's a combination of strength difference between those rocks, but my personal preference, I guess, as it were, is that the layering in mare materials, just like we see in sedimentary target rocks on Earth, plays a big role, and actually allows crater collapse to occur, and then shallows, that complex crater form. And we can jump ahead to look at a couple of good transitional examples here. So on the right-hand side is, a less busy plot of depth versus diameter again, and this is just for transitional craters on the moon. And two really great, wonderful examples are Giordano Bruno, perhaps the largest fresh crater on the moon, and then Picard. And so they're exactly the same diameter, 22 kilometers across, but you can see morphologically they are drastically different. Giordano Bruno is deep, and you can see that in the plot on the left. Perhaps one small terrace up there in the northeast corner, and then Picard has a number of terraces and is much shallower overall. And so this just goes to emphasize that craters formed in the highlands and then the mare have quite different properties. Okay, so back to this iconic image of the moon. We really glossed over this, or I did, a few slides ago when we were talking about excavation and ejector emplacement. And so I do want to come back to this for a second, because, when you look at Tycho, at least my eyes are just drawn to, Tycho, its rays, and its ejector deposits. And so, how is ejector emplaced? Well, for this, you need to come back to, a famous paper, a groundbreaking paper by Vern Oberbeck, who sadly passed away earlier this year, who coined the term ballistic sedimentation. And, I think this is one of those major discoveries that has stood the test of time. And so this idea of ballistic sedimentation and radial flow really does beautifully describe the emplacement of ejector deposits, ballistic ejector deposits, not just on the moon, but throughout the solar system. And so, what's going on here? So you've got the final crater the growing transient cavity on your left, kind of colored in black there. So you have the innermost ejector being launched first with highest velocity, and then the outermost ejector of that transient cavity is undergoing excavation, is launched later and with lower velocity. And so that is then deposited closer to the crater rim. And so this explains why at places like Meteor Crater, you see not a perfect, but basically a rough overturned stratigraphy. And the other important thing here, which is shown, I'm not sure if you can see my mouse, but you've got these three little boxes that are kind of snapshots, of course, because this is not a static process, of what that ejector blanket would look like at three different radial distances. And again, I haven't sought to modify this diagram at all. So this is the original from Oberbeck, 1975. And what you see here in these little diagrams is in black is VP. So that is the primary ejector derived from the transient cavity. And so it's important that, once this ejector lands, it does so with a portion of the impact velocity. So hence the word ballistic. And so this material strikes the surface, often at, several kilometers a second for high velocity impact. We've got 0.5 kilometers a second here in these diagrams. This then, because this material is traveling so fast and with so much energy, it keeps excavating some of the material from outside the crater. And so this is the concept of secondary ejector. And as you go further out in that ejector blanket, the amount of primary ejector becomes quite low. So it's often something I hear, people presenting in talks saying that, you can just take your ejector blanket and put it all back in. We can't do that. And of course, this is important for sampling. If you were to sample an ejector blanket, a lot of the material will be actually material from outside the crater. It will be low shock, and it will be material from, quite shallow parts of the stratigraphy. Okay, so, when I was a grad student, I kind of read this paper, and it's fantastic. That accounts for the formation of a continuous ejector blanket. But what about melt ponds? And so this was a discovery. Jim Head, our convener in New York, made in the 1970s. This is here. This is a Tycho crater, and you can see the block right ballistic ejector. But then you see these two low albedo ponds. With the advent lunar reconnaissance with the camera, and in particular the NAC images, you can confirm, we haven't gone there, of course, so it's not unequivocal. But for everything we know about, we interpret these ponds to be primarily impact melt. They must have clasts in there from what we know of the cratering process, and we see these beautiful. And importantly, this material overlies the ballistic ejector blanket. And so, how does that occur? Well, it's important to note that this is not just the moon. We see such two-layer stratigraphy on Earth, and there's two really good examples here. So on the left-hand side is an Austral crater in Labrador, which if you're looking for, a good lunar analog crater on Earth, this is definitely the one to go to, but because much of the target sequence there is amorphosite. And, it's a bit of a complex diagram, but the rocks are complex. But you essentially see classed poor melt rock overlying essentially this polymix, so mixed breccia. And on the right-hand side is a famous locality from the Ries crater in Germany, where again we see this two-layer stratigraphy. So this greenish swabite material overlying the reddish ballistic ejector. And so, I showed this cross-section earlier, but in reality, this is more realistic. And so here you have impact melt-bearing ejector overlying a ballistic ejector blanket. And so how do you get to where this occur? Well, we shared with you, an idea. It's still a working hypothesis here from 2011. And essentially, in the interest of time, I'll maybe skip to this stage. But because of this modification stage of crater formation, the collapse of the crater walls and the uplift of the crater floor, this can, after the emplacement of ballistic ejector, cause a second pulse or episode of ejector emplacement, where this melt-rich material that typically lines the interior of the crater can be emplaced outwards. And, this does scale up. When we published that paper, we weren't sure if this held for large basins. And so this is a paper by Zach Morse, a PhD student of mine, published this year in Icarus. And I'll just draw your attention to facies B and C here, that are basically these giant melt flows. And again, when you look at these big basins, scale is really critical and important. 100 kilometers across. So, this melt flow here in M, which is highlighted in the box here, was transported maybe 1,000 kilometers. In itself is, maybe a couple of 100 kilometers by 100 kilometers. Excuse my host going into the office here for a second. Okay, so this actually gets us now onto the products of impact cratering. So, hopefully we're going to be, and you'll hear from the NASA administrator next week about, the plans to go back to the moon. We, of course, have been to the moon, and we have some great suites of samples in the Apollo collection. And so when we look at Apollo samples, of course, most rocks on the moon that have been brought back, even the predominantly volcanic rocks, have been shocked to some degree. And so this gets us into the concept of shock metamorphism. And, very quickly on this slide, I just want to highlight that, we're basically talking order of magnitude higher pressures and temperatures than normal crystal metamorphism. For the geologists online now, if you, in your metamorphic petrology labs as an undergrad, you may have looked at rocks that were maybe 1 gigapascal pressure, but that's extremely high for Earth. And so, most crystal metamorphism on Earth happens in this gray area in the bottom left of this diagram. And then we get, into shock metamorphism or impact metamorphism, which takes us, up to over 100 gigapascals. So very quickly, shatter cones are the only macroscopic structures if you're an astronaut on the lunar surface. This is your eyes for shock. These are produced at pressures as close to 2 pascals, And then the upper pressure limit is something that we're not quite sure about. Moving up, we have planar deformation features. And so, that most of our actually comes from looking at quartz, which of course, as you'll know already, is not common or completely absent on the moon and most other objects in the solar system. So, it's something that we need to relook. The shock in feldspar and pyroxene definitely hasn't been as well studied as quartz. And so there's definitely room here for considerable more work. And, PDFs is a good example where if you look in the literature, people talk about planar deformation features in feldspar, but they typically don't say whether that's plagioclase or alkali feldspar. And, we've done studies where we've come up with not a single PDF in plagioclase. And so this is definitely a topic that deserves some further attention. Same goes for diplectic glass. And so this is not a sample from the moon because this is a sandstone on the left, but it's the best example I have to show the formation of diplectic glass. So, glass we typically think of as being quenched from the liquid phase. So you had something that melted, cooled quickly to form a glass. Whereas diplectic glass, at least we typically think of it the case as a solid state transformation, where you essentially, in a nutshell, have just broken up the crystal lattice so much that it becomes isotropic, but macroscopically it still retains its crystal shape. As I say down the bottom here, diplectic plagioclase feldspar is known as mescalonite. We do see this rarely in Apollo samples, more so in lunar meteorites and then in a lot of other meteorites. Its origin is controversial, as I put there, because there are some scientists in the field who are proposing that mescalonite actually forms from a melt too. And so again, if you're interested in pursuing this work, there's a lot of work still to be done, I think, in revisiting shock in lunar materials. Okay, in the last few slides, before I hand over to just want to talk a little bit about the particles that we have in the Apollo collection and that we see on craters here on Earth. And so impactite is a term for rocks produced, not just produced, but affected by an impact event. So, that shatter cone could be a site with a shatter cone in it, but we also call that an impactite too because it's been affected by shock metamorphism. So, very busy diagram. We can go over this, afterwards. Lots of different. This is just one way of classifying impactite. Is a topic of debate. But what I'll talk about, I think, quickly here is just impact melt rocks. So, impact melting is one of those, perhaps one of the most well-known products of impact events. We see this beautifully in fresh lunar craters. We have, samples in the Apollo collection. It's good to point out, because you've talked about lunar volcanism already, but just there are some major differences between endogenic melting and impact melting. Summarized in the table below, I'm not going to go through word for word. Key differences is that, unlike endogenic melting, impact melting is not a partial melting process. You're not melting part of a rock and extracting a little bit of that melt. It's essentially kind of whole rock melting upon decompression. And then another key difference is that impact melts are what we call superheated, so they're well above the liquidus temperature. Some recent work actually done at Mescalonite in Labrador suggests that these melts are at least 2,700 degrees Celsius and potentially well over 3,000 degrees Celsius. So having these hotter melts enables them to make a lot more mineral and gives them some different chemical and physical properties than, again, regular endogenic melts. And quickly now, what do these look like? Well, again, on Earth, we have the luxury of flying around in helicopters and looking at these on the ground. But the key take home here is that impact melt rocks look like igneous rocks. And so the left-hand image here is an impact melt rock. This is part of the melt sheet of the Mulstering Crater in Labrador. If you go to hope and see a column in about 30 meter cliff here. On the right-hand side, again, a couple of images, roughly a kilometer or two across. We can see cooling cracks in the top image, and again, beautiful flow textures on the side there. So they form sheet-like morphologies, just lava flows till the end of volcanism. It's very equal, especially when you only have a lump of rock hand, you don't have the outcrop to maintain something as being a volcanic, whereas it be an impact rock. And you can set in some rock scale. And so on the left again is the Mulstering Crater. In the center there are very coarse-grained rocks that you might be forgiven for thinking are intrusive rocks from Earth. But that is the impact melt sheet or the sub-impact structure. So that's the image of yellow rock there. Form mix of impact melt rock, and then also beautiful vesicular impact melt rocks in the bottom right there. You know, if we zoom to the next slide, this is all impact melt rock. Vesicular glass, fine grained. And I will draw your attention to this image on the left. This image just provided me back from the next course, I think at least once. This was a and then Clive used those software and suggestions were able to propose that this was in fact an impact melt rock. You can see how difficult it is if you don't have clasts that have shock metamorphic features in. It can be very difficult to prove that something is endogenic or stitch red. And the final slide, just kind of zoom in at microscopic scale. Again, if you gave that top left-hand image to an undergrad igneous petrology lab, I'd probably get a box for saying, no, it's an andesite, because it's exactly what it is. It just happens to have been produced by an impact event. And the textures, again, marine salts, we also see in impact rocks. With that, I'm not sure entirely we should take questions now or after Brandon's talk. We'll end there.
Okay, thanks, Oz. I think we'll keep questions until Brandon's done. Let me just add for everyone that Oz has been very active in the astronaut training for the Canadian astronauts, and he has, in fact, taken many of them into the field, so they have firsthand a lot of knowledge about this wonderful array of impact melt and other deposits associated with Canadian craters. So they're really well qualified to help teach the other astronauts, the U.S. astronauts, the other ones too, in this area. So they also get training. David Kring has been very helpful in that as well. So I guess David St. Jacques is about ready to launch, as I understand it, pretty soon here.
Absolutely. I think it was, I just heard today, might be moved up because of the last failed soil launch, so it might be earlier in December now.
Oh, excellent. Okay, so we'll stay tuned for that, and let me introduce Brandon Johnson now. Brandon received his PhD from Purdue University, working with Jay Malash, and he undertook a postdoc at Massachusetts Institute of Technology under Maria Zuber, and indeed he is now assistant professor, tenure track in Brown University Department of Earth, Environmental and Planetary Sciences in our Planetary Geoscience group. So Brandon has a wide array of interests, including a variety of things related to impact modeling, but also distal impact ejecta, taking a look at impact jetting, spallation, impact origin of chondrules, extrasolar system impacts, quite a diverse array of talents. So let me turn it over to Brandon.
All right. Perfect. All right, thanks, Jim. Thanks for inviting me to do this. And Oz, thanks for that great introduction. I was hoping you would hit all the points you did so that I can get right into the formation of impact basins. Okay, so this image here that we have is a LRO image of Oriental, and on the right side of it, you have Grail free air gravity overlain. And this is going to be, this as well as the recent drilling of Chicxulub are kind of themes of recent major advances in our understanding of formation of impact basins. Okay, so basins, understanding basin formation, as I'm sure you've already gotten from this class, but I'll say it again. Basins dominate the structure, tectonics, and stratigraphy of the lunar crust. So on the left here, we have Lola topography, and on the right we have Grail free air gravity. And so even in topography, it's no surprise we can see that the moon is covered in these large basins. But when you look at gravity, you can see that these basins are dominating the gravity of the moon as well, and that's telling us how they have really changed and redistributed crustal materials. So I'm going to go a little bit quick here because I'm trying to make up a couple minutes of time. So we touched on this here, the size morphology progression of lunar craters. So on the left, we have a nice simple crater. Then we go on to a complex crater. And let's see, I don't know. Oh, you can see the arrows. Okay, there we go. Oh, no, that's not me.
Yeah, we can see you.
Okay. Oh, there we go. Okay, so here we have a complex crater. Then we get up to a nice peak ring basin, and then on to mulching basins where we have, so the peak ring basin, we have an inner ring and then a rim. And then on the mulching basin, we have two outer rings and then an inner ring that's more similar to peak rings of smaller basins. So essentially, our understanding of craters gets worse and worse as the size of the crater gets bigger. And so at the smaller size, it's this very simple structure, and as we get bigger, it's very complicated. So some of the questions, I hope you can come away with some idea of what these answers to these questions might be, are what are these rings that we see, how and when do they form, and where does that ring material come from? So is this a good place to explore in the future potentially? So. Okay, so a little bit more detail about basin rings. We have some nice work by Baker et al. Showing the morphometry of peaks and rings. And so on the left is just showing kind of how these different things are measured. But on the right is really the more exciting plot, I think, is showing the central peak or peak ring diameter versus the rim crest diameter. And so what this shows is that as complex craters get larger, their central peaks tend to get wider. And then you have this transition to protobasins, which I don't have enough time to really get into the details of protobasins here. But then we get into the peak ring basins, and the diameter of the peak ring then continues to increase with the diameter of the crater. So this is probably telling us something important about how these basins form. Okay, so today I'm going to talk. So on the left, we've already seen some of this. So this is from Malash, 1989, in his cratering book. On the left is a few different time snapshots in the formation of a complex crater. And so Oz has already kind of beautifully discussed how this happens. You excavate a transient crater, then the floor of the crater comes up as the sides are collapsing, giving you this nice terracing. And you're left with a terraced crater with a nice central uplift and a central peak. And based on this increase in the size of central, the width of central peaks, and then the width of peak rings, the dynamic collapse model for formation of peak ring basins was kind of born out of that observation. And so in this case, the idea is essentially the formation is similar to the formation of a complex crater, which has a central peak, but the collapse produces a central peak that is too high. So it's not stable, and it's not gonna just sit there. So that peak then collapses, and you're left with a peak ring. My arrow's not really doing too much there. That's fine. Okay, so I'm gonna switch over to terrestrial craters. So Chicxulub is approximately 150 to 200 kilometer diameter crater, and on the top right we have the crater colored according to gravity. And just recently, so in April to May 2016, the IODP joint with ICDP, so that's the International Oceanic Discovery Program, and the International Continental Drilling Program. I think that the D was changed for the ocean program, but not for the continental program. Expedition 364 drilled into the peak ring of Chicxulub. And so Chicxulub, many of the craters on Earth are poorly preserved and don't tell us all that. They tell us a lot, but not as much as the morphometry of lunar craters. But when it comes to Chicxulub, right after it formed, it was covered up with a bunch of sediments, and so it's actually pretty well preserved. And so the peak ring was drilled. On the bottom left, we have some sense of what our thinking of what the structure of the peak ring of Chicxulub is. And so we have a crystalline basement at the bottom, and above that we have some Mesozoic sedimentary rocks that collapse into the transient crater. And then above that we have peak ring material. And that was the big question before drilling this. What is that peak ring material? Is it crystalline basement material that had collapsed over this sedimentary rock, or is it just sediments? And the reason we had that big question is because the seismic velocity of the peak ring material is relatively low, and so it could be consistent with it being near surface sedimentary rock. Okay, so we can look at simulations of how a peak ring basin might form. In this case, this is Chicxulub. This is from a recent paper that just came out, Euler et al. And this is this is going to show a simulation of a 14-kilometer diameter impactor striking a target at 12 kilometers per second. The target in gray is 3 kilometers of sediment overlying the kind of salmon color 30-kilometer thick granite basement, and then below that is mantle material. And there's this little blue patch of stuff that's tracer particles, and we're going to see that eventually becomes the peak ring of the crater. And on the top right is the same patch of material, and we can see how this material deforms over time. So as we form the transient crater, that patch of material stretches vertically, and then it collapses into the transient crater and makes a part of that central uplift, which is unstable, and it collapses, pushing out over these sediments and forming the peak ring of the basin. And so that in this model is essentially what was drilled during just in 2016 there. So this is the dynamic collapse model for formation of peak ring basins. I guess I'm going to play again, or we just have a little bit of a time delay there. Okay. So what did they find when they actually drilled into the peak ring? So the predictions of the dynamic collapse model are that the peak ring should be this granite basement material, and what they found when they drilled it is a bunch of granite basement material that was shocked to varying levels. And so I'm not going to talk about the details of the modeling, but the models show that the shock levels of the material should be anywhere from almost unshocked up to shock levels of a few tens of GPa. And so they see evidence for that in the planar deformation features in frame F there, you can see that, and shatter cones in frame G. So this is pretty spectacular that they were able to find shatter cones within this drill core. So it's pretty fantastic result for people who are excited about cratering and want to know how these basins form. So this is another result from Euler, and this is a really fantastic paper, I think, where they did this very detailed structural analysis of the core, and they found that the rocks tend to behave more ductily and kind of more viscously at early times in the crater formation, and at later times you start to get more brittle deformation and brittle behavior. And that's actually really consistent with this idea of acoustic fluidization for why these big craters collapse and form the way they do. And this is an idea that you have strong pressure vibrations, and that rock tends to slide when the pressure is relieved by these vibrations, effectively reducing the friction of the rock. And the melts that we're seeing are not consistent with frictional melts. They're actually intruded, essentially like dikes of shock melted material. so this seems like a really strong support for the idea of acoustic fluidization. It's just really fantastic. It's not something I would have thought we would be able to come to that kind of conclusion from this drilling, but I think it's really amazing stuff. Okay, so models. These models and observations of lunar basins also show some support for this dynamic collapse model. So this is some work by Kring et al., the same Kring who you saw at the start of the class. This is Schrodinger Basin here in this little white, see if I can get the arrow here. This little white box shows where this is kind of blown up on the right side. And using, I believe it was M-cubed, they mapped out different lithologies, and they found that the peak ring has a range of compositions ranging from kind of nearly pure northocite to norite and troctolitic kind of compositions. And this, they use this to suggest that the peak ring is kind of from a lower crustal or deep kind of crustal origin, but not necessarily mantle origin. And the models of the formation of Schrodinger show that you get, so this on the right here now, we're showing the formation of this crater in a simulation, and the material is colored according to its original depth to show you some sort of provenance. But what they found is essentially that the depth of origin of this peak ring material should be about 25 to 30 kilometers deep, and that seems to be consistent with our understanding of what we might expect to see for the composition of the lunar crust at those kinds of depths. And so not only does this give this consistent story, but it tells you if you want to learn about the interior of the moon, these basins and their composition are a good way to kind of get at that. Okay, so still going fast here to try to catch up. So moving on to Mulstering Basins. So really, the Grail gravity and Lola topography are amazing and have led to a real shift in our understanding of lunar basins, or real leaps in our understanding, I would say. And that's because with topography and imagery, you have a good idea of what's happening at the surface of the moon. But what Grail has done is it's let us get a look at the subsurface. And so on the right again is this LRO image with rear gravity overlaid. On the left is a nice artist's conception. So this is from James Keane, showing what we think Oriental kind of looks like on the interior based on Grail and Lola. And so from these data sets, we have this idea that the outer two rings are normal faults that cut all the way through the crust of the moon down into the mantle. And the innermost ring is more consistent with a peak ring, and that doesn't seem to show any real signature to great depth, so it's not consistent with a large fault or something like that. And in the center, we have this large-scale mantle uplift, and that's surrounded by a region of thickened crust. But that's really, that added constraint, I think, is the reason that we've been able to better understand the formation of these basins, because we know how crust was redistributed during the impact, and so we know what the final state of the basin should be like, and that is really has the important keystone in being able to try to understand the formation of these basins. Okay, so one of the ideas for how you can form mulching basins is the ring tectonic theory of mulching basin formation, and this is something that was proposed by Bill McKinnon and Jay Melosh in the 80s. What this plot shows, or this schematic is showing, essentially for frame A is if you have a very thick lithosphere compared to the scale of the basin. In this case, you don't get any faults that would cut through the lithosphere. So that's not, I guess, too much of a surprise. You know, the basin is very small compared to the thickness of the lithosphere. You can't get faults that cut through the lithosphere. Then we go to the frame B here, this is when the lithosphere is thinner compared to the size of the basin, and this inward flow of weaker material at depth causes you to get lithosphere breaking faults that are potentially the outer rings of lunar basins. Then going to frame C, this is not something that we see on the moon, but this is something that we see on icy satellites. This is if the lithosphere is very thin compared to the scale of the basin, then you can get several to many concentric graben or faults. And then D is, I don't think that's something we've seen anywhere, is if the lithosphere is extremely thin compared to the size of the basin, you actually get both concentric and radial faults as you have waves that actually go out into the low viscosity material. Okay, so I'm going to show some of my simulations of this. So I'm going to step through this and then show a few movies. So this is some work on the formation of Oriental. This is going to show a 64-kilometer diameter impactor striking a moon-like target. So the target is a big sphere that is the size of the moon, density of the moon, and whatnot. And the crust has a thickness of about 52 kilometers. And in this case, we have an impact velocity of 15 kilometers per second and a thermal gradient of 14 Kelvin per kilometer. The left side of this plot is the symmetry axis. So the base, you can see that the impactor is on top of the moon and it's cut in half. And so you can, if you want to think about what this looks like, you can reflect it across in your mind. And the material is colored according to total plastic strain, which is a way to show faults. So where we have really high total plastic strain in a linear region, that's where we would get a large normal fault. So 2.5 minutes into the impact, we have excavated a large transient crater. This is the maximum depth of the crater, not the maximum extent of it. About 180 kilometers deep. And you can see the crust mantle interface here. Then we move on to 10 minutes into the impact. We see that the floor of the transient crater is coming up, and we're starting to get a central uplift. And ejecta continues to be in place on top of the crust. Then going on 15 minutes into the impact, we have a central uplift that's over 100 kilometers high and about 200 or so kilometers in diameter. So this is a pretty spectacular event. We can start to see some indications of localized total plastic strain. We'll see next as we go to 18 minutes, 18 and a third minute into the impact, we have the formation of the outer rook here, and that's from the inward flow of this warm, weak material at depth. And this plot doesn't have any vertical exaggeration. I'll show you one with some vertical exaggeration in a minute here that kind of drives home that these are faults. But if you've seen enough of these plots, you can actually see there's some offset at the crust mantle interface and a topographic signature of the outer rook here. Going on to 25 minutes, central uplift is collapsing, but we still have more inward flow of material and formation of the outermost ring, the Cordillera. So the outer rook forms first, then the Cordillera in these simulations. Then we have collapse of the central uplift, making a bulge of material here, which then collapses to form the inner rook ring. And so that formation is very similar to what we think might happen for peak rings of smaller basins. And so I can briefly show you a movie of this. So I think without stepping through this, it's hard to, first, it would be really hard to see what's going on. In fact, I made that mistake early on at a few ground meetings. Jim can attest to that, I think, where people had no idea what I was showing them. So we get this collapse of the transient crater, this uplift forming. It then collapses, and you get this formation of the inner rook ring here. And then we'll watch this one more time, and as you'll see, the transient crater collapses. This inward flow of material is causing the formation of these two outer faults, and they have offsets of a few kilometers or so. So here's a zoomed-in version of that kind of plot. So this is vertically exaggerated. The left axis is the vertical axis is elevation. the horizontal axis is distance from the center of the basin or distance from the point of impact. And essentially, this is at 50 minutes, so this is after the inner rook form. But if you were to see this model before the impact, it would be a whole bunch of horizontal lines, and these lines are showing you material that was initially at the same depth. And so the inner rook isn't all that exciting in this kind of plot. You can just see that has a topographic signature and this kind of folded over crustal material. But you can see that the outer rook and the Cordillera, see the lines of material at equal depth all of a sudden drops down as you're moving in towards the basin center. And that drop down is the offset along the faults that we're pretty much resolving here. And so this formation is pretty consistent with the ring tectonic theory for formation of multering basins. And these models that produce rings in approximately the correct location give us great fits to the crustal thickness that's constrained by Grail. And actually, early on, our models that gave us the best fits to the crustal thickness of Grail started to show kind of ring structures, and that's why we started to really get into trying to look at the formation of these rings. So I think you can't really overstate how integral Grail was to this being able to simulate the formation of these basins. Okay, so I went fast enough, so I have enough time to get to the stuff the more recent stuff that I really wanted to get to. So this is showing the effect of impactor size on the formation of these basins. So this is the impact velocity of 15 kilometers per second, a surface thermal gradient of 13 Kelvin per kilometer, and a crustal thickness of 52 kilometers here. And the reason why I keep telling you about the thermal gradient is because that depth where you get warm, weak material and the thickness of the lithosphere are really important parameters in the formation of these rings. But what we see is at the top frame is a 40-kilometer diameter impactor, and we only get one kind of ring forming, and that's right at the rim of the crater. So this is not a mulching basin, this is just a peak ring basin. But if we go up to the 50-kilometer diameter impactor, we start to see more than one ring fault here, and that's actually consistent with where we expect the onset of mulching basin formation to be. So the smallest mulching basins on the moon are about 600 kilometers in diameter. So that is kind of a nice thing that our models that give us mulching basins also have this transition from peak ring to mulching basins with size. Then going up to even larger sizes, essentially the story is maybe not that wild, but it's nice to see that as we expect the peak rings of these basins move outward, and also the outer rings also tend to move outward as we increase the size of the impactor. Okay, so then just finally, so this is what I'm showing here is some results from a paper that was just accepted like a week ago, so you get a sneak peek. This is showing the effect of thermal gradient of the moon before impact. And so the 10 Kelvin per kilometer thermal gradient, you do get two rings, but they're not very much what we, they don't really look like what we expect for mulching basins. And there's not really anything that looks like a peak ring. As we increase that thermal gradient, where the peak ring forms moves outward, but we also see that what we were initially saying were rings, we start to see more of them, and there's not as much offset, so we're getting more and more ductile behavior, which again is maybe not unexpected, but it's really cool because we can potentially use the formation of mulching basins and these kinds of simulations to get an idea of what the thermal, the temperature depth structure of the moon was at the time these basins were forming. So, maybe not unexpected, but I think it's still really exciting and something for the future. So just to conclude here, I think the dynamic collapse model and the role of acoustic fluidization and formation of peak rings has really strong support from recent drilling of particularly peak rings. So that's why I focused on that model. I know that the debate probably certainly isn't over but that's a really great thing. This ground truth from this drilling. Models that resolve basin rings and reproduce Grail and Lola-derived basin structure broadly agree with the ring tectonic theory for multi-ring basin formation. And I think basins and the rings can tell us a lot about the composition as well as the thermomechanical state of planetary interiors. So I think there's a lot more we can do with these basin formation models and detailed observations. And then the last, modeling and observations have led to some major advances in our understanding of basin formation, but there's still a lot to do. There's still a lot we can learn. So, or no, I was hoping this would play. There we go. Okay. There we go. So I'll end with that.
So hopefully this is on continuous loop. So during the questions we
can listen.
Okay. Oz and Brandon, thank you very much for the very comprehensive and complimentary presentations, really excellent. So now we'll turn it over to Ariel Deutsch, who will address some of the questions that have come onto the chat group and in our class here. So chat box, so Ariel, take it over.
Thanks. And Oz, if you can go ahead and activate your webcam again, that would be great. Okay, so the first question that we have is, how can impact cratering be used to estimate crustal thickness, and how has it informed us about differences between the lunar near side and the lunar far side? So I guess either one of you can answer if you want.
I would say probably more Grail and gravity measurements have done more for that, as well as Apollo seismic experiments. Those are really where we get the estimates of crustal thickness from, and we use those constraints in our models. Compositionally, there might be something more to say. I don't know if Oz wants to touch on that.
Yeah, I think in terms of structure, I think you're right there, Brandon. But obviously, we can use, because of the nature of central uplifts, in the bigger the crater, moving from complex to peak ring craters, in theory, the deeper the material are uplifting. And so there's been a lot of work, using M-cube to look at central peaks in different sized craters to try and get a better idea of the composition of the rocks in the kind of the upper and lower crust.
So I'd add to that, too, that Brandon mentioned the seismic data from Apollo, and of course we've heard from previous speakers about the necessity and desire to have a broader scale seismic for both the near side and the far side. So that's something really want to keep that on our agenda for future missions, et cetera. Okay, Ariel?
Cool. So we have a couple of other general impact cratering questions. The first is whether you could touch on some of the main differences in the cratering process and the results for impact into a rocky versus icy planet. Brandon?
I can take that one, sure. So the process is actually pretty similar for smaller craters. We see a transition from simple to complex craters that scales with gravity. It happens at a bit smaller size on icy bodies, and that's not because the mill's a bit weaker. But then as the craters get bigger, we see a lot of things that are not seen on rocky bodies, where we see actually craters, their depths start to decrease as you increase the diameter of the crater. And that's thought to possibly be evidence of really weak material at depth. And then this whole, we do see mulching basins that look like rocky mulching basins on icy bodies, but then as we get up to even larger sizes, then we start to see these Valhalla class basins with several to dozens of concentric rings. So there it seems, essentially on icy bodies, the ice is rock, and on rocky bodies, the rock is the rock. So there's a lot of similarities, but there are some subtle differences.
Right.
Yep, for sure. And maybe just, one quick addition is, ice can relax over time. Fast rock will do too. There is isostatic, compensation, but obviously, ice will flow and you get viscous relaxation of craters on these icy bodies too. But yeah, overall processes are pretty similar.
Right. Speaking of relaxation, so we have a question from Chuck Wood. He asks, is the Austral Basin low ring morphology and shallow depth likely to reflect conditions when impact occurred or later isostatic accommodation?
Say yes. Yes.
Pass.
Well, yeah. Okay, guys. So I don't know, Chuck. I mean, my sense would be that basically, if the thermal gradient was such that it's going to have an influence during the formation event, like Brandon was talking about, then it's likely that that's a major contributor. It's hard to imagine heating up an area the scale of a basin with global thermal evolution or regional thermal evolution, and having it be related to the subsequent history. So my thinking is that maybe not for the topography. There's a wavelength dependence of topography and viscous relaxation. So the actual topography of the peaks themselves, it would seem to me that if those are much lower than the younger basins, that would almost certainly be maybe related to the event itself rather than longer term thermal accommodation, simply because of the wavelength dependence of that. I got a positive nod from Brandon.
This might be more of a dynamical question, but the question is the probability of impact cratering equal at all locations across the planet, or can the frequency or the size of the crater correlate with the position of a planet?
Position.
So there,
Go ahead, Brandon.
Okay, so there was so for the moon specifically, you might expect to see some difference in cratering. Essentially, you get sweep up of more bodies on a leading edge of the body, but I don't think we've seen any real evidence of that in the cratering record. So that being said, if you have differences in temperature structure, like on the moon, the near side in the PKT versus far side highlands, there does seem to be actually some significant differences in the formation of basins on those areas.
Okay, we have a couple of questions specific to Oz's portion of the talk. So the first is, you talked a lot about different geologic mapping that you and your students have done. Can you talk a little bit about the difference between identifying impact melts versus volcanic melt ponds on other planets as well as on Earth?
Sure. Yeah. It's we talk about it a little bit in the. I think Jim shared a recent review paper on impact melting, and we go into it a little bit there. For this, I think it is slightly easier, we've found, because the Marais deposits, the volcanic deposits, typically are more iron-rich. And so, even using Clementine data, we've been able to differentiate, dark, smooth-looking material, the more iron-rich volcanic deposits from impact melt deposits. I'd say remote sensing for the moon is perhaps a bit more straightforward. You've got very little overprinting. And, when you've got the crater there and you can trace out melt flows and things and everything makes sense, that's one thing. I think in samples, that's where it gets really difficult. Most of the Apollo samples are not from outcrops or even from individual boulders. They're just lying around. And of course, in meteorites, it's even more complicated because you don't know where they're from. And so there, when you've got a fine-grained, volcanic looking rock, it can be next to impossible to differentiate whether it's endogenic, volcanic, or impact. But that's where, we're now looking for new techniques to differentiate. Again, I mentioned Clive Neal's group's done some work on using essentially the distribution of sizes of plagioclase feldspar, and that seems to be a very interesting approach. Geochemistry, again, if there's evidence for superheating, that's one. But yeah, it's not easy when you're just looking at samples.
Aria, this is David Crane. Can I chime in on that?
Yeah, of course.
Absolutely, David.
A couple of times we've heard allusion to the issue that the Apollo samples are complex, and that's definitely true for those that we've obtained from the Apollo missions. And for that reason, I think there's a very strong argument when we go back to the moon, or when we go to the moon again, that we go to the two youngest basins, that being Schrodinger and Orientale, and collect samples in situ. There you can collect samples in outcrop or very close to their original source locations and see what a primary or first generation impact melt and impact melt breccia looks like. Then we'll be smart enough to begin interpreting rocks associated with older impact basins on lunar surface.
Well, thanks, David. The next question, Oz, is you spoke at the end a little bit about the mineralogy and petrology that can record some of the impact process. Are there any processes that can erase these features?
Yeah, things like the shock metamorphic features that I showed. Time, even on Earth, the Sudbury structure is a good example. So, even that same event that formed a shock metamorphic feature, like a planar deformation feature, if those rocks stay hot enough for long enough, those features will get annealed out. It'll be less important on the moon, but on Earth, hydrothermal fluid flow and alteration will rapidly, weather glass into clays, and again, just anneal out things like planar deformation features. So yes, the older the crater, whether it's on Earth or the moon, the harder it is to see those primary shock metamorphic features.
Thanks. So a couple of questions for Brandon about the drilling project you spoke about. So you spoke about the shock fluidization in the ring structures of Chicxulub. The question is, are those shock features related to the high energy imparted with such a big impactor that leads to the basin, or would you also expect these features in other smaller impact structures as well?
Oh yeah, if you could get really detailed structural information, like from the drill core, there may be some way to get at this for smaller basins if they're really well preserved. I think it's preservation is really the hard part there. Dave Kring might be a better person to ask this question.
Well, if I can add, go ahead, David.
Yeah. So I've been part of these Chicxulub studies since the beginning and part of this project. So let me say that the samples that we see in the core have been shocked, as Brandon said, up to about 20 gigapascals. And so many of all of the shock metamorphic features that we see in that granite would be found in any impact crater that saw similar shock pressures. So that's the type of thing you might see in one of the Clearwater craters, the Reese crater. Many craters preserve lithologies with those that saw those shock pressures. Now, the expression of the shock features is going to be dependent on the lithology, whether it's sedimentary, whether it's crystalline, if it's coarsely crystalline or finely crystalline, so those will be different. The other thing that maybe to point out, since we're supposed to be talking about the moon, is that we oftentimes talk about shock monomorphism on Earth in the context of granitic-like rocks that are quartz-rich. We have quartz on the moon. We actually have quartz-rich basalts, but quartz is not the strong indicator mineral in lunar impact lithologies as it is on Earth. So
another question about the drilling project. if models can predict peak ring crater formation already, what was the new information that we wanted to learn specifically for drillings? For example, did the cores confirm that the proposed physics from the models is correct?
Yes. so there's been a lot of debate over the years about how peak rings would form, and the drilling project, I think, has been a strong affirmation of the dynamic collapse model, and so the models predicted that, but until you go and see a peak ring in this great detail, it's just a model, and you need that confirmation in the actual observation.
Okay, a couple of questions about.
Yeah. Oh, Ariel?
Yeah.
Can I jump in one more time?
Of course.
So, the results from in the new Euler et al. Paper absolutely are consistent with acoustic fluidization, but it also illuminated a terrible problem in the way in which acoustic fluidization is modeled in the hydrocodes that Brandon was showing you. There's used what's called the block model approximation. And the block model approximation in those computer codes that seems to work uses a block size that seems to be far larger than what we actually see in the core. And so some new physics need to be added to that block model to make the codes work and reflect what we see in the core.
And I would say that's a really good example for everybody listening of the iteration you get from proposing models, essentially testing them, and then going back and refining models until you reach closer and closer to an approximation of reality.
That's a great lead into our next question, which is directed at Brandon and asking sort of what are the aspects that you think need the most improvement for the hydrocode today? So what are the model's biggest weaknesses or different physics that still have yet to be incorporated?
Oh, there's a lot. I think David was touching on this acoustic fluidization. We have a very the idea itself is somewhat controversial. So to see that this seems to be what is happening in reality, but not only that, but getting some more insights into how that works. There's a lot that can be done to make these models more accurate and get them working a lot better. In addition to better models of acoustic fluidization and the transient weakening of rocks, we have things like we always need better equations of state, which describe how the thermodynamics of the rock responds to shock pressures, better strength models and constituent relations. Rocks are very complicated, and trying to model how they behave under these extreme conditions is not easy. So there's lots of work.
And I think this is another good example here, because what it's saying is, of course, as Brandon pointed out in the last point in his last slide, is there's a lot of work to do. So listen to that list and think about how you and your own work can really start to supply some better data to put into these models. And again, with the observations on the Chicxulub core, I'm sure there'll be a lot of things that will come out of there. We'll be scratching our heads on that we can think a little bit more about how those observations can help constrain the models.
Great. Brandon, in one of your simulations, you showed an impactor velocity of around 15 kilometers per second. One of our questions is, what's a reasonable range for impactor velocities on the moon? And also, what are some of the changes you expect for your simulations when you do vary this impactor velocity?
Yeah, so the range, I'm going to blank a bit on this. I know it can go all the way down to 2.4 kilometers per second, but there's not many there. Kind of the peak is around 18 to 20 kilometers per second, but if it's a comet, it might be 40 or 50 kilometers per second. So it depends on what you're talking about, but I'd say 15 to 25 kilometers per second might be a reasonable range. But we're simulating vertical impacts, and so a lot of times what we do to better represent, get some kind of approximation of an oblique impact is you take a fraction of the, essentially the vertical component of the impact velocity to get at that. But if you were to decrease the impact velocity, you'd probably get, you'd have to have a bigger impactor. You'd get a little bit less melting for the same size crater probably. Same thing if you increase the impact velocity, you get more melting, more heating. So it could have some effects on the final crater morphology, but probably more towards the center of the basin than in the outer part.
Okay, and then for Oz, related to some of the schematic models that you showed at the beginning of your talk, illustrating the cratering process, we had a question on how you might imagine these impact models needing to be adjusted for heavily cratered terrain. So the question is, will a cratered terrain show the same impact behavior as a smooth terrain?
I mean, that's a great question, and I think, Brandon can vouch that, that's probably a long way off in these numerical simulations, is putting, a lot of topography on the surface. For the big basins that he was looking at, though, is probably less important. But we do see that, for craters tens, even a few hundred kilometers across, that topography does play an important role. Impact melt, for example, is a good one where melt flows. It's like, especially because it's superheated, it will have a viscosity lower than water for a time, and so perhaps the early stages of cratering will be independent of surface topography, but where that melts and where the products end up, we've seen that time and time again on the moon. That if there's low topography in this region, the melt will pour out of a crater in the topographic kind of downrange direction. So yeah, it definitely plays a big role, and it'd be a very hard thing to add to the models, but maybe someone will do it someday.
Okay, we have one final question, but it's rather grand, so maybe you can both take a stab at it. It's, how do the cumulative effects of small crater impacts and basin scale impacts result in the porosity, density, and thermal structure of the lunar crust?
That's so easy. I'll let Brandon answer that.
We're working on it. Some of our initial findings. So we've included impact fragmentation and the formation of porosity through tensile failure into some of these models, and they seem to actually be pointing towards that. A lot of the porosity is generated by basin scale impacts, but then that subsequently you have kind of localized production of porosity by smaller impacts, and then if the porosity is too high, then an impact will actually crush out porosity, so you kind of get this equilibrium that happens. But this, Braille has shown us what the crust of the moon looks like, and now we're trying to understand why it looks like that.
Anything to add, Oz?
No, I think that's a great answer, and yeah, on a small scale, from looking at sedimentary versus crystalline, we've seen the types of things happen that Brandon has mentioned. So yeah.
Okay, I had one final question, which has to do with the concept of cell secondaries. Many of you know that a lot of things have been mapped in which you see an apparent excess of small craters in the interior and in a rim of some young impact craters, and the interpretation has been that that is related to very high angle ejecta that doesn't essentially re-impact the surface until the crater is virtually formed. So watching this simulation here, I know there's some edge effects in here, so I was just wondering how you see that from essentially a modeling point of view. Are there aspects of the model that fit the idea of cell secondaries in terms of timing and location of their interpretation?
Yeah, so Mike Zanetti, I think, has done a lot of great work on mapping this and putting this, really showing that cell secondaries are a thing that we need to understand. a really interesting problem, and I think the best ideas I've heard so far are, if you have pre-existing topography, you can, maybe that can cause you to get some ejecta that's at these very high angles. But it's certainly not something that we see in our current models, and so it's a big problem, and I'm sure it will tell us something very important and interesting about the cratering process, but I don't know what that is yet.
Okay, so for all of you students out there, yet another thing to work on. We need all the help we can get in understanding this, and I want to thank Brandon and Oz for a very excellent set of presentations. And again, to remind you that these are recorded, and you can go to the website to refresh your memory or alert friends that they might want to take a look at this excellent set of presentations. So let me say just a couple of brief words in closing here. The first is that, of course, next week the NASA Administrator, Jim Bridenstine, will be talking to us, so I'll send out a note about that. Have your questions ready. In fact, if you want to send any ahead of time, let me know and I can make sure they get forwarded to him as well. I've already forwarded a few related to kinds of things that I'm sure you're interested in, how you can participate in commercial missions, and also what's the timeline for getting astronauts to the moon. I mentioned that to him because I know you all want to be in that position. So that'll be a question I hope he will address. If not, you can be sure to ask him. One last thing. Last night, my wife Ann and I went to see First Man, and I just want to encourage you to let's just think about this. How to put this? Actually, save your money. Okay. I worked in the Apollo program, and new Neil Armstrong. This was not the man I knew. This is not the program I worked in, and it's certainly not the moon that I know to exist in terms of its portrayal, particularly the Apollo 11 landing. My God, if you now armed with this idea about the size and morphology relationships, the relationships of morphology as a function of size, I encourage you to go back. Well, actually, don't waste the money, but anyway, if you happen to have seen it already, try to place into the diameter distribution of morphologies the crater that Neil purportedly landed in the movie, because it looks to me somewhere between 25 and 40 kilometers in diameter. So trust me, there was nothing like that there. Anyway, Dave Scott, the Apollo 15 commander, sent me an email today, said, hey, listen, he was, well, I won't go into that, but he said there's a BBC as well as National Geographic are putting out in the coming year 2 really good biographies and analyses of Neil's life. So I encourage you to take a look at those, and I'll certainly, as soon as I learn the schedule for those, send those around as well. So it's amazing. Signal of noise, a lot of noise, low signal. Okay. Anyway, that's an endorsement, and you heard it here first, okay? Okay, so thanks very much for everybody, and we're looking forward to next week when we'll talk to Administrator Bridenstine. And thank again Ricky Guest at SSERVI Central, as well as Brandon and Oz. We're signing off now. Thanks a lot.